Okay, so there's a new tutorial for this week. I think it's easier than the last one because there's nothing that you need to implement on the IPGA board. These are basically just simulations, and most of the work are repeating. Just try to practice with all the memory blocks. So today I'm going to talk about the latches, the structure of the latches, and how to use them really quick. So you understand why we programmed it that way or modeled it that way in the tutorial. So there are several different structures of the latches and flip-flops. And towards the end of the tutorial, you can see these are examples of the memories. Basically, it's ROM. It's a read-only memory because we pre-write all these binary numbers or hex numbers into the memory file, and then we read them out using Verilog. So the major command we are using for Verilog is read mem. If it's a B followed by B, it's a binary memory file like these ones. So it knows that every single line, every entry is a binary file. If it uses a read memory H like this, so Verilog knows that it's reading a hex memory file from this file and read it to this variable in your Verilog, in your model. So you can see these are hex numbers, although it don't look like a hex number, but they are, right? A to F, right? So all these letters can be used as a hex number, right? So what is D? 13, right? Right? 13, 14, 10, 13, okay? So these are hex numbers, keep in mind. And we're using an IP, a memory file from the Vivado modeling tool. So there's a image file you can download from the website, which is the ds_image.coe. That's an image file, and you read that image file into your ROM, in the IP. So the tutorial tells you how to find out this IP and how to load the data, preload the data into the memory, and how to read it out. All right, and follow until here, and it shows you part of the test bench. So your final, the task 3 over here is to finish this test bench and read all these data from that image file after you load it into this memory block. So eventually this memory block will be written or implemented on the IPGA board. It's going to be a physical digital block. It's a memory storing all this memory, the image file data in the memory. And then what's that?
Are the IPs like just a collection of modules that other people have written?
Yeah. It's just a sub module. So you can see in your test bench, you can instantiate it, right? After you create it, it's automatically generated by Vivado. So in that case, you'll see a name of that module generated by Vivado. You can see the name, and then you just instantiate it in your test bench, right? Your test bench. So the name of the memory is my ROM, okay, and you name it as U. I just give it a new name, and then get all the ports listed and connected to your sub module, right? So you can see when you are creating this little IP in Vivado, it right shows you the ports, right? Shows you the ports. So since you know this is going to be a sub module of your test bench of your top, so that's why in here, right, you do a dot this, and dot clock. You are connecting the memories ports to your another sub module you write in there. Yeah, all simulations. There's no physical implementation to the IPGA board for this tutorial, and this is due about 12 days from now. So I think the pressure level is okay. Okay, because we have a lab next week. Okay, so the lab could be a bit tricky. So that's why we covered the details about the lab on Tuesday, and I'm going to talk about more details about it today as well. I'll directly type all these 2 sub modules for you guys in the class, and so you guys can repeat it, just duplicate it, can directly use it. And so So Tuesday next week will be a midterm review. I think we'll just slow down and give you guys a lot of examples to prepare for the midterm exam on the 20th. All right, Thursday. But in between that, there will be another new tutorial regarding VGA ports. And there's another homework 4 due Friday, which is tomorrow. You're thinking, oh, all the tutorials are so difficult, couldn't make it. But eventually, it's a really simple one, only a couple of 2's complement problems. The goal is to prepare you guys for the lab next week. Okay, so the homework 4 due tomorrow, keep in mind, it's not a long tutorial, it's not a lengthy tutorial. Okay, it's only a couple of problems. I think I already posted in Canvas. I'll take a look at it later, okay? Just a couple of 2's complement problems. It could be critical, you need to know how to deal with those problems in order to complete your lab next week. Okay, so on Tuesday next week, there will be a quiz 6 on 2's complement. Okay. So if you can finish homework 4 by Friday, and I'll give you a quick review. Turn it in, I'll grade it. I'll give you some quick review on Tuesday at the very beginning of the lecture, and probably around like 9-ish on Tuesday, I'm gonna let you guys do the quiz. So you guys should be prepared for that. Okay. After do the homework and after the review on Tuesday, you should be able to do it. Okay. So first, let's look at the structure of the latches. So I believe it's been a while. A lot of you probably already forgot how this works, right? So the structure of this circuit is called SR latch. It's SR latch. So for the SR latch, looks like this. You can have 2 NAND gates or 2 NOR gates. They'll do the same, very similar job. Doesn't really matter which one you want to use, right? But usually NOR gates are a little bit slower than NAND gates. But just looking at this structure here, NOR gates, for example, it's feeding back to the input of the next one, and 2 inputs. Just to remember what does R mean and what does S mean here?
Reset and set.
Yeah, reset and set, right? Reset and set. So if you look at the structure here, if we give a because they are inverted, right? Inverted. So I'm assuming they have to be different. Okay. So 1 0, for example, at the very beginning. 1 0 at the very beginning. So 1 is being fed back to So 1 is being fed back to here, 0's here, all right? So 0 or anything is what? It's still this thing, okay? It's still this signal line. So we cannot get a definitive answer here. But what about 1? Because 1 for the input of the OR gate, even though it's the NOR gate, but it's still OR, right? So it's 1 or anything will be 1, and inverted is getting a 0. Okay? 0 comes back to this port, but it's still uncertain. So in that case, we need an input for here as well. Okay, we need an input for here as well. So in that case, which one? Even though I'm showing this figure here, right? So you can see this R is S, this R is S. A lot of times you can forget like which ones should be R, which one should be S, and which one should be R. How do we verify it? Start from the input instead. So assuming that for the latches, you don't give the same input at the same time. That's just a rule. That's a way to use it, right? They have to be inverted for most of the time. There's just only one case you give a same input for this NOR gate latch, which is using a memory mode, to get into the memory mode. But now let's assuming that the 2 inputs are different, okay? What's gonna happen? Are we getting a definitive answer here or no?
No.
It should be, right? Because one or anything, doesn't matter what signal here is. One or nor, doesn't matter. Nor anything. One, right? One. Nor anything is what? 0. Okay, so this becomes 0 for sure. No doubt. So 0 comes back to this port. All right, you got 2 zeros. Definitely you are getting a definitive answer here. What is it? No, has to be 1, right? So 1 comes back to this port. 1 nor 1 is what? 0. Okay, so the electrons are going through all these wires like crazy and really fast, almost the speed of the light, right? Eventually it's latching the 2 results here to Q and Q naught. And it's stable. It's not changing, okay? That's why it's a latch. So if you give a different input, what's gonna happen here? Where should you get started? Wherever you have a 1 as the input, because whenever you have a 1, you know exactly this one has to be 0. Okay, 0 comes back to here. 0, 0 is giving you a 1. So the way we define which is S, which is R is, if we turn on that pin, Q is being set or reset. Did you learn this in logic? So which one should be set? Which one should be reset, and why? If you don't look at this figure here, why is that? Right? So which pin should be R, which pin should be S?
1 should be on.
So either one can be 1, right? Like I said, if that specific pin or input is turned on, right, which means I give a 1 to it. If I give a 1 to it, okay, and Q, we're looking at Q. If Q is set, then that pin is S. If Q is reset, then that pin or input will be R. Okay? So when I turn on this pin, Q is set or reset? Set. So if I turn it on, Q is set. And that's why this has to be S. Okay? Look at here. If I turn on this pin, give a 1 to it, Q is set or reset? Reset. So this has to be R. Okay? Same circuit. RS. So it's SR latch. Works that way. Okay? So we assume the Q is on the top, right? So Q is the output on the top. Then the pin on the top, on the left-hand side, as the input will be R, right? Just keep in mind for the NOR gate latch. For the NOR gate SR latch, it's gonna be RS. So in that case, we don't usually use 0, 0. And why is that? Because the inputs, whenever you are using the latch, you can control the inputs. Okay? So if the inputs are 0, 0, 0, 0 are still being used. Let me draw the truth table. S, R, Q, Q naught. 0, 0, 0, 1, 1, 0, 1, 1. Okay? So definitely, these are the normal operation. Okay? Normal operation, we give a 1, 0, I'm getting a 0, 1, I'm getting a, if I give a 0, 1, I'm getting a 1, 0, which is good. Okay? So these are normal operations. However, for this NOR gate SR latch, which one shouldn't be used? Which set of input shouldn't be used? You probably have heard about this a lot in logic. 1, 1 shouldn't be used. Why? Because 1, 1 is going to give you what? 0, 0. There's no information. It's all these NOR gates or OR gates are killing that whatever information you had previously. So and we are defining Q and Q naught, right? We hope these outputs should be Q and Q naught, so they are useful for some kind of circuit design. Eventually, if you give it 1 1, okay, if you give it 1 1, a lot of times you heard about this in logic. Like, why shouldn't we use it? Is it burning the circuit, or is it illegal? Why? It's actually not doing anything but giving the two outputs zeros, which make it useless. But it's not burning it, right? It's okay. It's kind of they could be digital inputs like 1 1, but the thing is, it's making this whole circuit useless. So 1 1 is unused. What about 0 0 though? 0 0 is doing what? So previously, you just have to have a legit or useful information. It could be 0 1 or 1 0, doesn't matter, right? And you are generating an output being latched as the output, and immediately after that, you switch both pins to zeros. What's gonna happen? 0 or A is what? Still A, right? 0 or A naught is what? Still A naught. So it's not changing the result. Sorry. Yeah, right? 0 or A naught, still A naught. 0 or A is A. It's not changing it, not changing the result. So whenever you have a, for example, 1 0 as a previous, the last state, and then you switch the input to 0 0 after 0 1, okay? What's gonna happen is it's gonna memorize the two results, 1 0 over here as it's gonna latch it as the output. It's not changing. So 0 0 input for the latch is a memory, state. It's being used for the NOR gate SR latch. If you are using a NAND gate SR latch, it's going to be different, slightly different for the logic, but very similar, okay? Very similar. So since we know the behavior of the SR latch, so these are the inputs sometimes we can see possibly, and these are the outputs we need. It's like a user's manual, right? But regarding like why do we need it, it's something else. It's going to be a different story to talk about. But now we just need to know how this is being used, all right? It's either if you want to set Q, you give a 1 here, give a 0 here. If you want to reset Q, you give a 1 here, give a 0 here. That's how you use it. A lot of times you don't even need Q naught over there. So Q naught is not even the port. So a lot of times you're just using Q as the output. You are setting or resetting, and it's able to latch it as the output. How? You just give 0 0 to the input, and no matter how things go, I mean in the circuit, it's gonna latch the previous result over here. If you give a 0 0 in the memory mode, if you operate in the memory mode, it's gonna remember the previous state over here. So it's latching the previous results as the output. Make sense? That's how we use it, and let's see how we model it in Verilog. For the SR latch, so the sensitivity list is S or R. Does that make sense? Is there a clock? Nope. The two inputs are the only two signal lines you have. So it's either S or R get changed. You want to change the state, right? If the inputs don't change, definitely the outputs are not going to change. Otherwise, it's a disaster, right? Nothing changes from the input. The output keeps toggling. What's going on, right? So these are inputs. If they changes, it's gonna update. It's gonna update all the logic over here. Okay. So see if S. So if S, it's the same syntax in C++. So if S is 1, right? So if S is set, you are giving what? 1 0. Why 1 0? Because you are setting Q. So Q has to be 1. Okay? You are setting Q. Else, if R is 1, you are setting Q naught, or you are resetting Q. Okay? That's the behavior we just talked about during through the truth table on the paper. All right. What about other cases? We need to model other cases. Because we assume that you are not giving that unused inputs, I think. You can definitely include all four cases on the truth table, right, to here. But the goal is we assume that the inputs are legal inputs, okay? So whenever we see a S, it's like a command, right? It's like a command. If we see S becomes 1, we just set it, okay? Just set it. It's asking us to set it. If you see a 1 to S, just set it. It's running a simulation here, so we're giving 2 different inputs and trying to look at the outputs, okay, Q and Q naught. For SR flip-flop, it's adding a clock stage in front of it, and what you need to know for this structure is the clock is it's not an edge triggered flip-flop. It's not an edge triggered, it's a level triggered. Draw the figure on the paper. Is it AND gate or NAND gate? AND gate, okay, AND gate. Latch inputs have one extra control layer here. QQ naught, and I want to let you guys tell me, okay, if I add one extra layer in front of it and I'm using a clock to control it, which one should be R, which one should be S? If I give a 1 here, what's going to happen? If clock is 0, what's going to happen for the AND gate? Yeah, 0 and anything is going to be 0, right? So it's killing these AND gates. You're getting 0 zeros. 0 zeros are what? Memory. Okay? So what's happening is when this clock is running, when clock is 1, right? When clock is 1, it's a level trigger, because when clock is 1, whatever changes you're having here will be passed through the 2 layers of gates and reach Q and Q naught. But whenever clock is 0, it's a memory, right? 0, 0 is a memory. Really nice. Okay, so whatever you had previously when the clock is on, clock is 1, will be memorized when the clock is 0. Why do we need that for this? Why do we need that? So it's actually latching the results at the outputs, which is really useful. For example, when clock is 0, doesn't matter if these signal lines are changed because of noises, because of any other things and undesired inputs or something like that. Doesn't matter if clock is 0. Why? Why doesn't matter? The NAND gates are being killed, right? So it's getting zeros no matter what you have as the other 2 inputs. Okay, you are always getting zeros. So remember, 0 on the truth table are memories. Okay, so what's happening is right before the falling edge of the clock, no matter what you have at this moment, okay, will be latched at the output. Because this clock signal right before the falling edge, clock is still 1. So whatever RS, SR, the values are, doesn't matter. So that input will give a certain output, and that output will be latched at these 2 points after the falling edge. So no matter what signals are getting toggled after that point, it's not affecting the results of the output. Okay, but still, this is still not a very good design because the level trigger. The thing is, during this level, during this high voltage level, or logic 1 level here, okay? So this signal can change a lot of times. It can change from 1 to 0, 0, 1, whatever. And all these signals will, the outputs will reflect the changes from the input, okay, during this period of time. It's only latching it at this moment, right? It's like telling the inputs, just get ready, right? I'm gonna latch you at the output. It's still trying to go back and forth. Which one do I prefer? And change back and forth. Eventually, at this moment, whatever the inputs at this moment are, it's going to be latched at the output. Okay, still not a good design. Okay, because it's level triggered. Usually, we don't use level triggered flip flops. It's just very low cost, only 4 gates, right? So we prefer edge triggered, because when the edge arrives, so for example, here's your data. No matter what is your data, okay, looks like. If it's an edge triggered, we know exactly that at this rising edge, at this moment, this data will be latched. Okay, really sharp edge. Okay, we'll latch it to the output. But level trigger will be different. Like all the level when its clock is high, right? So all the D values, okay, here, will be duplicated to the output. Okay, like that. Right? Y here is 1 for the output. Because it latched this point's value over here and keep it for the extended period of time. Because 0 is a memory. Okay? A little bit more difficult to control compared to the edge triggered if it's a level trigger like this. However, we can still model it since we know how it works, right? We know how it works. We can still model it in Verilog. Now let's take a look. It's really simple. So clock and S has to be 1 at the same time, right? So now you are adding another signal, an extra signal over here, because the clock is also controlling the output, right? Clock has to be 1 in order to perform a SR latch. Otherwise, it's just a memory. Okay? So if clock and S, which is set, right? So clock is 1, that's a prerequisite. It has to be, it's required in order to normally operate your SR flip-flop. So clock has to be 1, and S is 1. So when clock is 1 and also S is 1, which means you are setting Q. See? You are setting Q. It's operating normally. Okay? Else if clock has to be 1 again, and R is 1, and then you are resetting Q. For this bit, you are resetting Q. I feel like there should be an else, right? There should be an else. But that making things complicated, right? So I have to look at the previous state, what the previous state is. Yeah. Yeah, it's not a perfect example from the textbook, I think. I just model it and simulate it and see if we can clock the input, right? So that's the goal. D flip-flop or D latch. Okay, this is actually D flip-flop. Shouldn't be called a D latch. It's a level trigger D flip-flop. D means data. Okay, D means data. Why do we call it D flip-flop instead of SR? Because we are shorting S and R using an inverter. It's not actually shorting, but we're inverting S and R, so they're always different. They're always different. And D is labeled at S. So D will be Q, Q will be D whenever clock is on. And let me know if that makes sense to you guys. So D flip-flop is the data flip-flop, which means when clock arrives, or for this level trigger is when clock is high, right? Data is being passed to Q. That's why it's called data, right? So data is being passed to Q because Q is D, D is Q. That's the D flip-flop. data flip-flop. Why? Because D is S. Agree with me? D is at S. Okay? So S and R has to be inverted anyway. If D is S, when D is 1, you are setting Q, so Q is 1. Okay? When D is 0, since R is getting inverted, so R has to be 1. So when R is 1, Q is getting reset, so Q is 0. So which means when D is 1, Q is 1. D is 0, Q is 0. That's why it's a data flip-flop. Does that make sense? Because D is at S. Okay? D is at S. So that's why it's called D flip-flop. D flip-flop. You are getting rid of 2 entries from the truth table. Very simple. Just one line, right? When clock arrives, when clock's high, just give D to Q and D naught to Q naught. You can see Verilog makes everything easy because they're telling the system what you need, right? If you have this input, you need this certain output. Just tell Vivado to do it, right? You don't have to worry about the bottom level circuit design. And you can have an edge trigger D flip-flop because every time it's being latched to this point first, and then whenever the next rising, if this is rising edge, it has to be falling edge. So when the falling edge arrives, it latches the D in the middle to Q. Is that boring? Does that make sense? I probably want to run. I don't have a simulation LT Spice here for you guys, but I think if you are in the ISI class, probably 2 weeks from now, we are going to run some simulation for D flip-flops. But for this one, the first D flip-flop is a level trigger. So whenever this is on, and it's getting inverted for the clock for the next stage, so this is off. So in that case, the D will be passed to here and being latched here. The second one is getting disabled because of the inverted clock. Doesn't make sense. I know. It's difficult to imagine what's happening for the circuits. That's why we need the simulations, right? So let's see how we model it. Since we need a rising edge of the clock to do something, so when clear arrives, we clear it. Clear Q and Q naught. We clear Q and Q naught becomes 1. And when we don't receive a clear signal, so we are not resetting Q naught. We are giving D to Q and Q naught D naught to Q naught. So Verilog side of things is really simple. Okay, and the rest are writing into the memory, and then you read it from using Verilog. And that reading command is the $read mem b. Okay, so you have to manually type all the numbers in here, but in Vim is easy because a lot of times you can maybe just duplicate and copy and paste. Okay, you can see that memory file, you save it as memory.mem, mem, and save it in the same directory. Okay, you have to load it, have to add it at the source, to a design source. So this command will copy whatever in here into your variable that I can use in your Verilog, which is mem. And that is why we are having this line here. CE is a chip enable. If the chip is enabled, it's just a selection, right? So it's selected. And read enable is 1, so we are reading from the memory. If this is true, right, this is true, we're trying to access the memory file with this address. Otherwise, just give a 0 to the output. That's how we read it. Okay. So this one read it into this file. Okay, and then in your Verilog code, okay, it's trying to look at this command. If this command is true, you access to this certain address of the memory here, which is over here, and assign it to data. Okay, that's how that works. You can see the memory file has certain number of lines. So the address start from the top will be address 0, and keep adding, incrementing by 1. And you are going to write a for loop to go through all the addresses and read them out by doing this in the top. Because the monitor statement here is just trying to display a certain signal lines in your simulation result. So what kind of signals you want to display in your simulation result? So the rest are just snapshots. Okay, it should be really simple. Simulation only, okay, for this one. It's prepare you guys for the softcore, for the VGA one later, at a later time. So we're loading an image file to Verilog and trying to display it to the monitor. All right. Let's look at the code for the lab next week. Here. Okay.
This is a very quick demo for the 3-bit adder and subtractor. It's a little bit
Can see
these
the
ones on
results.
and give a 100.
So if you give, it's a 3-bit calculator, and if I have, couldn't tell, 1 I couldn't tell actually, I'm sorry, but eventually the goal is to display the 2's complement results of either addition or subtraction and convert it into either positive numbers or negative numbers. And if it's a negative number, you need to add a sign in front of it. Okay, that's the first task. And the second task,
Right, this is a quick demo to the 3-bit subtract.
is to use shift register to load the A's instead of directly doing adding a subtraction, additional subtraction with the B's, but you are using a switch. So I believe I used this switch, number 13, as the data, and I'm using this one as a clock. So what's happening is I have a little shift register, which is serial in and parallel out register, 3 bits, inside the IPGA implementation, and I'm using this switch as a clock, right? So it's detecting a rising edge of this clock to latch the serial input, whatever the input is at the moment, to the queue of the D flip-flop. So what I'm gonna do is I switch it on, so it's providing a rising edge, right? So that whatever the data is at the serial input at the moment will be latched to here. Okay. If I do another one, you can change the input at the moment when you do for the second time, but you don't have to change it. If you don't change it, you're having a 1-1 here. Okay. If you change it, it becomes a 1, and this one will be shifted to the right because the shift register is D flip-flop. So it's gonna pass whatever I hear to Q. Okay. If you change it to 0, for example, and next time it's gonna shift 0 to the right, and the 1 previously stored here will be shifted to the right. So you're getting a 0-1. Okay, and then you change this one to 1 again, and you move this clock, give a rising edge, and eventually this becomes 1-0-1. So you are providing a data or 3-bit binary number to A's by using a serial input instead of parallel from the switches. So you can save pin resources of any digital design in the future. Okay, so it's a serial input, it's a shift register, serial in, parallel out, and you need a clock. You need a clock to control it. That's task 2. So seems to be pretty challenging, and I'm giving you I'm going to type the debounce block of the Verilog code and also the shift register today in the lecture. Okay, so you can directly use that part of the code and directly make the connections to your 3-bit adder and subtractor circuit. Okay, and that circuit design I think is available somewhere. I'll probably give you some examples. Let's see. Yeah, let's start with the debouncing circuit first. Okay, debounce circuit first. Let's come back at 8:45. Give you guys 4 minutes break. Then we're gonna start our coding. Okay. So for task 1, it's just basically just the 2's complement, subtractor, and adder, right? Since we need the display on the LEDs and the 7-segment display, so if we treat the FPGA board as a top, we will need that a display module, adder module first. I'm sorry, adder module first. Because the adder is gonna give us the 4-bit output over here, 1, 2, 3, 4, including all the S, like S0, S1, S2, and C final, right? C2 final, for example. And remember, the logic for C2 final is something, right? We covered on Tuesday, the C2 final. So these are the results. So adder is just doing addition, okay? Just do the job, and eventually output all the results in 2's complement. That makes sense. And the adder takes input from the switches. 1, 2, 3. So it's gonna be switches. For example, the B's. Okay, B's. B2, B1, B0. Let's do switches from 5 to 3. And also need switches from 2 to 0 as well as the A's. A2, A1, A0. And always need a clock. Behavioral modeling is always better. Just being clocked and being controlled, right? So if clock's not here, don't do anything. Okay, don't do anything. Wait until the clock's here. So synchronizing everything, which is great. So clock. What else? Just think about the adder, right? Not a decoder yet. Not a decoder or display module yet. I think that's it. Oh, you need a C-1. C-1, which is a carry in. It could be another switch. Let's say switch 15, for example. And we need a display module. Display module. So display module is a decoder that controls the 4 bits input. And you need, because the display module, so we need to connect to SAG, right? SAG is from 6 to 0. And you need AN, which is AN 3 to 0, because 4 units, right? And you also need decimal point. So decimal point is just 1 bit, right? It's DP. It's a hardware resource. It's a keyword. Anything else? LEDs, right? LEDs. you're expecting how many LEDs should be directly from here, because this is already the 4-bit binary outputs, right? So you want to look at the LEDs output in binary form as well. So LEDs could be from 3 to 0 for the results. And because I need to connect the output of one sub-module to input to another sub-module, so I need a wire here. I need a wire here to indirectly connect them together. And the same thing, so since I have a wire here already from the top module, so I can definitely connect these 4-bit LED lines to this wire, because you declare wire from the top, right? I call it digit wire or something, and that's 3 to 0. Okay, you can declare this one in the top. Eventually, you have this one in the top, and you are making, in your instantiation of the sub modules, you are making connections. For this one, connect to this one connect to this, and this one connect to this as well. Or you can directly assign, right? Assign to assignment. LED equals do this at the bottom of the behavioral modeling. Okay, so every time clock arrives, it updates all the signal lines. Okay, so if this is getting updated, and this will be given to LED 3 to 0s, this will be updated as well. So it's included in the always block, but not getting engaged into any of the if statements, because this is always getting updated every time the rising edge clock of the clock arrives. What else for this display module do we need? I don't think so. It should be pretty much everything. And because this one may have an overflow indicator, remember we derived the logic expression for this overflow indicator, which is C1 XOR C2. Okay, so you can definitely have a port here as well. If you're curious if you have an overflow happens or not, so you have a LED number 4 to show an overflow indicator, which is helpful. Okay, that's it for task 1. So how do we code it up? Let me use VS Code. Recently, Control Shift or Control L, I forgot. Oh, Control Shift, so you can turn on the terminal. Okay, so if I enter documents, I got a folder here for Verilog files, and you can see I got a bunch of examples. So if we start coding, for example, the adder, start coding the adder first. Okay, see the adder. So I'm gonna start a new file, same as a Vim. I do a code. I just name it test. Okay, so look at the ports. Definitely module, test, what do you need? So clock first, do the easier ones first, okay? Definitely you need a clock. Because eventually all these ports will have to interface with the IPGA resources, right? Pin resources. So definitely need a clock. So you know what? So we can make it easier by doing this. Okay. I make it larger. I cannot make it larger. I'm sorry. So we can start input clock. And you can see these ones are A and B's, right? So A and B's. I can start with, input. Imagine that A is a 2 to 1, a 2 to 0 has 3 bits. They'll be directly shorted. So in your top, when you instantiate this module, so there will be a dot A parentheses switch something, okay? 0 B. This is going to be B plus A, right? A and B's. If you look at this line here, you need a carry in as well for the adder. So it has to be input CM1. Okay. And I can imagine that later in the programming, you have to deal with the overflow, and you are assigning values to overflow. It's latching that value to the overflow indicator. So the output for this guy is better to be a register type, same as digit. It's from 4 bits, right? 4 bits. All right, that's all the ports we need. Oh, this has to be called digit, I believe. Okay, save. Right? So digit covers the output over here. Overflow is the overflow indicator over here. CM1 is the input, clock is the input. That's all the ports for this module. So before we add more register types, we probably will find out we need more registers later. But now I think we can directly start the behavior modeling. For example, always add post edge of the clock. Okay. Begin, end, start new line, tab. Okay, so what do we need to put in here? When clock rising of the clock is arriving, what do we want to do? Just to do the logic, right? If you look at the adder's structure, you don't have to wait, just directly do it. We derived some of the logic, I think, on Tuesday. Okay, so you can still refer to the notes over there, but now let's just start typing into it. Okay, so you may need the intermediate values, register types for the A's and B's, because you are using A's and B's for a certain operation. We can start doing that. So for example, the first one for this circuit, so when A's and B's comes in, these are ports, right? These are ports receiving value from the switches. And immediately you are having an XOR logic to the CM1, which is a carry in. So you want to deal with that first, and eventually giving you another type, a different type of A depending on the carry in. If carry in is 1, you are getting a inverted, right? Inverted A. If carry in is 0, 0 XOR A is still A. So it's XOR logic, but you have to write it, otherwise Verilog doesn't know how to do it. Okay, so in that case, if I name, these are the ports are A's. If I name these ones, for example, AA's, right? So these ones has to be a register as an intermediate variable. So in that case, I find out, hey, I need something else in the middle. So probably I need register 220 and AA in the middle, right? And let's deal with the following ones first. So first, it has to be AA0, the first one. That one has to be equal to, let's use a procedural assignment. So that one is the input A, right? And that one XOR your CM1. Okay? You have AA1, right? Similar. And AA2, similar. Okay? What else? If you look at the circuit here. So we have completed this part. The thing is, we need C1 and C2 to find out overflow, so we need to get a separate signal line for C1 and C2, right? C0, I don't know yet. C2 can be a result of the certain combinational logic, so we probably need a variable here for C1 and C0, okay? How can I make this bigger? It's not visible, right? Is it visible?
Control plus.
Cool, thanks. So A is done. A is done. What about carry outs? The carries. That comes from the logic of the FA, right? So the logic of the FA is, let's see, S equals A XOR B XOR C in. C out equals A or B, C in or AB. That's FA's logic, okay? FA's logic. You got AB, C in, and that's C out and S. Right? You just have to do this for every single stage. How do we do it? So if you start with C0, I'm labeling this as C0, okay? C0. So what is C0? Let's figure out C0 first. C0 is what? C0 is what? I have to show you everything, right? Perfect. What is C0? Look at this one. Is that perfect, right? Show the windows on one monitor. What is C0? Based on the signal lines, the names over here. What is C0? What is A? A8, right? A is basically AA, this line, right? So AA what? A0. Do what? Or, right? Or. Oh, and. Wait, is it and or or? Or, right? Or what? Or B0. Do we have B0 declared? Yeah, it's just signal line from the switch. And directly use it. I cannot directly use A because A is not being used for this module. That's why we have to use the AA here in the middle, right? So it's a AA. Look at this one. It's a AA or B, parenthesis, and what? And what? C in. What is C in? CM1. Or A and B. So what is A? AA0, right? What is B? B0. Okay, done for the first one. Make sense? AA or B and CM1 or AB. Just in case, put a parenthesis over here. Okay? Question on this? No? Totally lost? Really? Questions on this before we move forward?
Can you explain again why we need an intermediate for A and not B?
Yeah, because B is directly feeding into this flatter, right? B is directly being used.
Oh, I see.
But for A has to XOR with the CM1 in order to get a input for the flatter first, right? Good question. Can we deal with C1 for now? Yes, let's do it. C1. I'll let you do it. C2. Is that fair? What about S0? S0. Do I have S declared? I haven't. So I need a register type, right? 220 S capitalized, and I also need a C2. C2 can be declared here, right? OV, overflow.
Why do you say S is 3 bits and not just say C is 3 bits too?
Since I'm separating all the C's, you definitely can. I think I'm not seeing any issues with that. I'm not seeing any issues with that. You can definitely do it that way. Yeah, it's gonna work. You can declare C's as a vector, no problem. Good catch on that. Okay, and we also need a C2 final. Remember, because the C2 has to be modified, and the C2 final equals something else. We just have to deal with that later. So I'm gonna code up this S0 for you guys first. So what is S0? If you look at this one, AA, right? XOR what? B0. XOR what? Cool. Start a new line. Capitalize the O, shift the O, right? Start a new line in Vim. And you can have S1, S2, right? So that's pretty much everything for the adder, because the adder is doing what? The adder is taking the input and giving you S and carry outs. That's it. So we take in the inputs, which are the AAs, and it's giving you all the carry outs in the middle and also the S as well. But for this specific adder, we also need a overflow indicator, right? Overflow indicator, which is OV here. It's not 0V. Keep in mind, it's OV, overflow. So the overflow indicator is C1. Remember we derived the logic last time? It's a C1 XOR C2. And C2 final is something else, right? C1, we derived it last time. Just look at the notes. Okay? So if you have C2 final, because the results is combining, do a concatenation using C2 final as an MSB, and S3, S2, S1, S2, S1, S0 as the following, the lower 3 bits. So if you, for this line, the line 24, right, can get your C2 final. So the next step should be like doing the concatenations, right? You can combine C2 with all the S to form a the final result, okay, and give it to digit, right? So you need an if statement. Remember, if overflow occurs, we want to use what? this is interesting because we already find out the logic for C2 final, so we don't have to do an if statement. Remember? It's already done. C2 final is already done because it's already takes care of all these different conditions. That's why we use the C2 final. Otherwise, we just use the C2. Remember 2's complement? 2's complement, right? If do what? Adopt C2, right? That's the conclusion from Tuesday, remember? And we derived as logic. Let me show you the truth table here. Okay, so C2 final is over here is a column on the right hand side. And we find out this column according to the overflow indicator and C2 and S2. Because when overflow occurs, we are using C2 as a final result. When overflow doesn't occur, we duplicate S2. That's the rules we are following, right? So by looking at the three columns, we are finding C2 finals. So if we already know C2 finals, what C2 finals are, so we don't have to do this if statement anymore. Okay, if you don't have C2 finals, you probably have to do a if statement, if else. If overflow is 1, do something, right? If overflow is not 1, it's 0, okay, you place S2 in front of it as MSB for the final result. So in that case, what can you do here for the Verilog? So after this line, C2 final is already available, right? What you can do here? Right? Can directly use it. Any question on this? Okay, so now you are getting the results. I think after you have the results, that's the whole mission of this adder module. You already have the overflow indicator, you have all the logic to give the digit result. Right, so you can wrap it up. So you have always begin end, you have all these kind of intermediate values, and eventually you need one more thing here, which is end module, save. Okay. Display module, how do we deal with that? Display module. Display. Let me open a new one. VSP display test.v. Right. So if you look at the paper here, display module, let's close it. Okay. So definitely it has to take in the digit data from it, from the adder module, sub module, and then output sag, an, dp, right? And not LED, but 3 outputs and 1 input. But it's also being clocked, right? So definitely you need input clock. It's being clocked. Everything's being clocked, right? and input is taking in from the digit from the sub module. So it has to be 320 and digit, which is here. Okay, and then output, you need a reg tab to hold the values for sag, and that one is actually 7 bits. And output reg, you need a 4-bit, AN, right? You also need a decimal point. So these are the ports. Look in the ports. Okay, so it's basically just a decoder. Just a decoder. And because we want this guy to be clocked as well, so it's always at pause edge clock and O, begin, end, shift O, tab. Display module, okay, display module. So what we need for display module. So it's taking the digit input. So digit input, right? Depending on what C2 final is, you can find out if it's a negative number or positive number. If the negative number, you have to display a bar in front of the digit, right? So how to deal with that? So definitely you need a counter because it's still scanning through the 2 units, right? The 2 display units back and forth, do it very quickly. So whenever it reaches the counter max, it could be a very small number because it has to scan really fast, so your eyes cannot resolve it. So in that case, you definitely need a counter and counter max. I don't know the exact values for now, but definitely you need a counter max, right? And that guy could be it shouldn't be very big. I mean, probably. Let me see what the value I use. I use the 16-bit decimal number, 64,000. And definitely you need a counter to count through that. So it's going to be a register type counter. And usually the counter, if your counter max is 16-bit, definitely you need a 16-bit register counter as well. So it's going to be 15 to 0, I guess. And then counter, right? Save. Okay, so then you have something to start with because when counter reaches counter max, you want to do something, right? So eventually, if counter reaches counter max, what else do you need? What other conditions do you need over here? When counter reaches counter max. So when counter reaches counter max, you need to do something. That's what you know, right? For now.
Reset the count.
Definitely you want to reset the count, right? Yeah, definitely. That's something. So begin. Definitely that's something you have to do first, right? That's a good strategy. Do the easier ones first, right? Definitely you know it has to be clean, have to be cleared up. So giving a 0-2 counter. But if the condition is good enough, just one condition, do you need something else? Because whenever it reaches the counter max, you are going to assign values to it. But you don't know which one is being activated for now. There are 2 units. If the first one is getting activated, you have to give a sign. If the second one is getting activated, you have to give a number. Right? So, yeah, so
The C final is 1.
so the, let's say, it's a logic, right? It's logic. It's not a bitwise logic. It's based on the events. let's deal with the first one first. If the first one is getting activated, which means AN1 is what? Is 0, right? Four units. This is AN1, AN0. Okay, you're only displaying on these 2 units. So you need to give a 1 in order to what? Disable it. And you need a 0 to enable it. Okay, 1 is disable. 0 is enable. Okay, so if AN1 is 0, which means that one is activated. Okay, so I need to throw a sign to it, right? If this guy's a 1 here, right? If this guy's a 1 here, then so which means if AN here is enabled and also C2 final, which is the MSB of the digit, is the 1 is negative number. What I want to do here?
Set the bar.
Set a bar. So sag has to be what? Something, right? I'll let you do it. All right. Don't turn in an assignment with XXX in your results. What else do we need to do? We need to shift AN because this is the only chance you can shift it, right? So how to shift it? So let me show you a technique over here. If you don't do it, probably won't be able to understand. So it's I'm assigning a intermediate AN, which is a rect type AN, because you cannot shift the keywords. So I'm declaring a AN with the same length, so I can shift AN. Okay. So it's AN equals so this is gonna shift. This is gonna shift the. Is it going to shift it or no? So the goal is to shift the 2 bits, activating 1 at a time. Oh, this is not shifting because it's still the same. Why do I have to do this? No, it's wrong. Sorry. So I'm swapping 0 and 1, right? So I'm putting 1 here and 0 here.
Isn't that the same thing?
No. Oh, yes. Sorry. One more time. So every time I'm swapping 0 and 1, right? Bit 0 and bit 1. So this time it activates this guy, next time it activates this guy. Okay? If during this if statement I activates this guy because this is 0, right? If this is 0, so it probably has to be ANN here instead of AN. Okay, so if ANN is 0, which means the second one from the right is activated, I want to swap it. Doesn't matter which one is activated, but next time, whenever next time it arrives, it's updating itself, AN, the lower 2 bits will be swapped. So I'm entering the next state, which is the other one will be activated. So I'm gonna, do another if statement after this. Okay. So, what are other conditions? You don't want to do anything until this one equals count max, right? So it has to be this first. And then,
Not and one.
yeah. It could be a positive number, right? So we want to, if this guy is activated and digit 3 is 0. Okay? I'll keep working on this probably next Tuesday. There will be 2 more modules that I have to show you guys how to do it as well. So we have to do it one more time. Take some time on Tuesday next week. All right, we'll see most of you later this afternoon for the VLSI lab.